Are you looking for complete past paper solutions with explanations that a mere mark scheme or examiner report won't give you? Are you looking for a quick revision of the entire syllabus with an explanation of the latest paper formats? If so, you are in luck, because with this video, Conquer Chemistry presents to you a new series of videos called Solve It. So without further ado, let's get started. Assalamu alaikum everyone, this is Fahd Ansari and I'm here to help you conquer chemistry. In this first video in our Solve It series, we will be solving the Cambridge International AS and A level paper 1, which is the multiple choice paper that AS level students take. So this is the specimen paper for examination from 2022, and previously the MCQ paper was only 1 hour long, but now we have an additional 15 minutes to solve it. It still consists of 40 questions, and all of them have 4 options A, B, C, and D, and you have to pick one correct option. And in previous paper formats, the last 10 questions would have 3 statements, and you would have to select a certain combination of those 3 statements that would be correct. But now those questions have been eliminated and we have simple, straightforward A, B, C, D 4 option questions. So before we begin, just wanted to remind you that over 70% of you still haven't subscribed. And if you're one of those people, don't hesitate and push the subscribe button, push the bell button for notifications so that you do not miss any new video. So without further ado, let's get started. So first question says, which molecule contains 8 bonding electrons, right? Now, this is important. It says 8 bonding electrons, right? And normally people get confused and they start counting bond pairs, right? Now remember, this is not talking about pairs, this is talking about electrons, right? So 8 bonding electrons, this actually means 4 bond pairs, right? Each pair has 2 electrons, and 4 times 2 will be 8 bonding electrons. So let's look at all of these structures, starting with option A. So carbon is bonded to the 2 oxygen atoms using double bonds. Now you can see over here we have 4 bond pairs, and that means 8 bonding electrons, right? So 2 bond pairs over here, 2 over here. So that's 2 plus 2, that gives us 4 bond pairs. And that means 4 times 2 is 8 bonding electrons. So option A is correct, and I don't need to go further to confirm from the other options. In question 2, it says that in identical conditions, the angle of deflection of a particle is proportional to the charge to mass ratio, right? So over here it says that in experiment, protons are deflected by an angle of positive 15 degrees. So protons have a charge to mass ratio, an E by M ratio of +1, that is the charge, divided by 1 unit, that's the mass, and so you have a charge to mass ratio of +1, right? So if I place the angle alpha over here in the ratio with the charge to mass ratio, the angle is positive 15 degrees and the charge to mass ratio is +1, right? Now it says in another experiment, under identical conditions, particle Y is deflected by an angle of -5, right? So now in the new ratio, I will write -5 degrees as my angle of deflection alpha. And so the charge to mass ratio needs to be found. So this will be my X. Now I can cross multiply. Because this is direct proportion, I could do this. And so X turns out to be, if I calculate this, this is going to be -5 times +1 divided by +15 So this turns out to be -1/3. So this is my charge to mass ratio. So now for this, first of all, I need to realize that this negative sign means that particle Y has a negative charge, right? Particle Y has a negative charge. That means it will have more electrons than protons, right? So let's figure out which options have more electrons than protons. So option A has 1 proton and 1 electron, so they're both equal, so this is incorrect. Option B has 3 protons and 5 electrons, so over here 5 is greater than 3, so I could consider this. Option C has 4 protons and 1 electron, so over here the situation is reversed. This is not what we want. We want more electrons. Over here we have more protons instead. Option D again has 4 protons and 3 electrons, so this is also incorrect. So option B stands correct, and we can confirm using the charge to mass ratio. The charge over here will be +3 for the 3 protons. You add to it the -5 for the electrons, that gives you -2. Mass over here will be just the protons plus the neutrons. Each of them has a mass of 1 unit. Electrons, remember, have a pretty much negligible mass compared to the protons and neutrons. So if I divide the charge by the mass, I will get -2 divided by 6, so that is -1/3. So that is the same as what we found out using ratios. So option B is correct. Now question 3 wants us to find the relative atomic mass of the sample of lithium, right? So what we do is we take the relative isotopic masses of these two isotopes, which are 6 and 7, right? I'm going to multiply the 6 by its isotopic abundance of 7.42. I'm going to do the same process for the other isotopes. So it's going to be 7 times 92.58. Add these two products together and then divide all of this by the sum of the percentage abundances, right? Now remember, in this case, it turns out to be 100, but sometimes it can happen that it is not adding up to 100. So always add up the isotopic abundances that you are, in fact, using in your calculation. This will give you the relative atomic mass, or AR, which turns out to be around 6.9258. And so we need the answer to 3 significant figures. So I'll round this up. I have 5 over here in the 4th significant figure. So I add 1 to the previous significant figure. This becomes 6.93. So it's going to be option D. So this is about the allotropes of carbon, which are diamond, graphite, and Buckminster fullerene, right? So which statement is correct for all 3 substances or all 3 allotropes of carbon? Bond angles of 120 are present. Okay, so this is not true for diamond because diamond has carbon atoms, each bonded to 4 others. So the carbon atom in the center has 4 bond pairs and 0 lone pairs. So according to the Vesiper theory that you've studied for shapes of molecules, this will be tetrahedral with a bond angle of 109.5. So no 120-degree angles are present in diamond. Option B says delocalized electrons are present. Again, not true for diamond because if you look at the central carbon atom, all 4 valence electrons are used up in bonding. So there are no electrons left over that can be delocalized. So option C, giant molecular crystalline lattice structures are present. So this is true for diamond and graphite, but not true for Buckminster fullerene. Buckminster fullerene has a simple molecular structure, right? Because each molecule consists of only 60 carbon atoms, so that's not enough to qualify for a giant structure, right? These are small, simple molecules with weak van der Waals forces between them. So option C is incorrect. So that leaves us with option D. Sigma bonds are present. Remember, all of these are different forms of carbon, which is a non-metal. And so there will be covalent bonds. And wherever there are covalent bonds, there are always sigma bonds present. So in this question, a metal has a total surface area of 150 squared centimeters. It is evenly coated with silver. By electrolysis, its mass increases by 0.216 grams. So it asks us how many atoms of silver are deposited per squared centimeter on the surface of the metal. So first step is to convert the mass of silver into moles. So we have moles of silver. This will be the mass divided by the AR of silver, because we know that silver is a metal and metals are considered to exist as single atoms. So we divide by the relative atomic mass, and this gives us this many moles of silver atoms. The next step is to convert the number of moles into number of atoms. So the number of silver atoms, we multiply the number of moles of silver atoms by the Avogadro constant, which gives us the number of atoms per mole. And this will give us this number of atoms, 1.20 into 10 to the power of 21. Then it says per squared centimeter. So what we will do is divide the number of silver atoms, which we found, by the area of the metal in squared centimeters. So this will give us 8 into 10 to the power of 18 silver atoms per squared centimeter. And so option A will be correct. So nitrogen has a higher first ionization energy than oxygen. Which statement explains this observation? Right. So nitrogen has a proton number of 7. So its electronic configuration is 1s2, 2s2, 2p3. In the case of oxygen, however, we have 8 electrons. So this becomes 1s2, 2s2, 2p4. Right. Now I want to focus on this last subshell. So 2p, in the case of the nitrogen atom, it has 3 orbitals, and each orbital has 1 electron only. And in the case of oxygen, we have 4 electrons distributed between 3 orbitals. And so what happens is each orbital is filled with 1 electron, and once all orbitals contain 1 electron, we start filling it up with the second. Now, the oxygen atom, the electron to be removed comes from this orbital that contains electron pair repulsion, also known as spin pair repulsion. And this is because we have 2 electrons repelling each other with the same orbital, right? Despite the fact that you have opposite spins, you still have spin pair repulsion. And because of this, the electrons already have a high amount of energy. So to remove an electron from this orbital, you need a lower first ionization energy, right? So in this case, option C, oxygen has paired electrons in the 2p subshell. This will be correct. So which molecule has the largest overall dipole moment? Well, in this case, it's not going to be option A because it only contains bonds between carbon atoms or carbon-hydrogen bonds, and we know that CH bonds are considered to be non-polar, right? It's not going to be option D either. The reason is that you only have 2 polar bonds in this entire molecule, right? You have these 2 CCl bonds where the chlorine is more electronegative, so it gets the partial negative charge. So you have a dipole pointing this way and a dipole of an equal magnitude pointing this way, right? And over here, if I look at the carbon atoms in the double bond, Each carbon atom is bonded further to 3 other atoms with no lone pair, so this will be a bond angle of 120 degrees, and so will this, right? So that tells us that this dipole and this dipole are equal magnitude but opposite direction, and so they will cancel each other out. If I place them over here and over here, these dipoles cancel out, and so you will have an overall non-polar molecule, right? Now that leaves us with options B and C. Now in option B, the only polar bond you have is the CO double bond, and this has a dipole facing the more electronegative oxygen atom. The remaining bonds in this molecule are non-polar, so we will not consider the dipoles there. In option C, you have the same carbon-oxygen double bond that is polar, but you also have carbon-chlorine single bonds that are also polar. And this carbon atom in the center is bonded to 3 other atoms with no lone pair, so this is bond angle of 120 degrees, right? So if I place these dipole moments, these vectors, try to sum them up, then I will have these smaller carbon-chlorine dipoles placed over here. This one I will place over here, following the head-to-tail rule for adding up vectors. And then I will finally place this vector that is larger than the other two, so I will have a vector sum that is equal to this small bit over here. And this is smaller than this dipole over here. This vector is much larger in magnitude, and so it's going to be option B that has the largest overall dipole moment. So question 8 over here says we have 2 moles of an alkane. This produces 665 cubic decimeters of carbon dioxide measured at 400 Kelvin and 1 × 10⁵ pascals. Carbon dioxide can be assumed to behave as an ideal gas under these conditions. So for this ideal gas, we have been given the pressure, we have been given the temperature, both of them are in SI units. We have been given the volume, but we need to convert this into SI units of cubic meters by dividing by 1,000, right? So the ideal gas equation is PV equals nRT, and we know everything except for N. So that's what we're going to find. So this becomes N equals PV over RT. So P over here is 1 × 10⁵, right? And the volume will be 665 divided by 1,000 because we're converting it to SI units of cubic meters. Divide this by R, the ideal gas constant, which is 8.31, and the temperature, which is 400 kelvins, also in SI units. This will give us 20 moles of carbon dioxide under these conditions. Right, so it says 2 moles of an alkane will produce 20 moles of carbon dioxide. So that means that the ratio between the alkane and CO2 will be 1:10. That is simplified from 2 moles to 20 moles. That gives us 1:10. Right, so 1 mole of alkane gives you 10 moles of CO2. And remember that all the carbon in the alkane forms CO2, right? So as a result, this alkane will contain 10 carbon atoms, and so we have option C, decane, which is the alkane that we're looking for, which contains 10 carbon atoms. All of these will react with excess oxygen. This will react with excess oxygen in a combustion reaction to give you 10 moles of CO2 for the 1 mole of the alkane. So which expression gives the standard enthalpy change of combustion of methane, right? So let me write the equation for the enthalpy change of combustion. So 1 mole of methane is going to undergo combustion with oxygen, with excess oxygen to give you complete combustion products. So we have CO2, 1 mole of that, and 2 moles of H2O. So if I balance this equation, I'm going to get 2 moles of O2 over here. Right. We have been given enthalpy changes of formation in all of these options. You have enthalpy change of formation given, right? So to find the enthalpy change of combustion of methane from this equation, all we do is we're going to add up the enthalpy changes of formation of the products. And then from that, we're going to subtract the sum of the enthalpy changes of formation of the reactants, right? That's the simple method of using enthalpy changes of formation to find enthalpy change of a reaction. So in this case, we have enthalpy change of formation of carbon dioxide, which is added once because you only have 1 mole of it in the equation, plus 2 times enthalpy change of formation of water, because you have 2 moles of it in the equation. So you have 2 enthalpy changes of formation. Subtract from this the enthalpy change of formation of methane, and that's it, right? There's not going to be any enthalpy change of formation of oxygen because this is an element, and the enthalpy change of formation of an element from its, element is going to be 0. So enthalpy change of formation is going to be 0. So you don't include this in the equation. So this expression matches option D. So option D is correct. So now we have a redox reaction containing chlorate 1 ions over here. So from the name chlorate 1, that tells us that chlorine has a +1 oxidation state. So that means option A or option C will be acceptable, right? And chloride ions, Cl negative, obviously it's -1, right? And both A and C have -1 and -1, so we have to calculate the oxidation state of chlorine in ClO3 negative. For this, the more electronegative oxygen will get its usual oxidation state of -2, and this will be X, right? So X plus 3 times -2 for each oxygen. This will add up to give you the charge on the ion, which is -1. And when you solve this, turns out that X is going to be +5. So this is going to be option C, which contains +5 for the chlorate in ClO3 negative. So in this question, another redox reaction, and this is between MnO4 2 negative ions that are reacting with water to form MnO4 negative ions, right? So over here, the Mn has an oxidation state of, we'll have to calculate this. So we have 4 oxygens, right? So that'll be 4 times -2. And over here for Mn, this will be a simple X, which you add to this, and this will give us a sum of -2 for the ion. So this actually gives us +6. And we could do similar sums for MnO4 negative, which was going to give us +7, and MnO2, which is going to give us +4 for the Mn in this particular compound. So now we need to balance this equation using changes in oxidation number. So you can see that Mn goes from +6 to +7, so it's being oxidized. It also goes from +6 to +4, so Mn is also being reduced. So this over here is a disproportionation reaction because the same element, manganese, Mn, is being oxidized as well as reduced. Right, so in the case of the oxidation, it goes from +6 to +7, so that is an increase of just 1. But when it is being reduced, goes from +6 to +4, so that is a decrease of 2. So change of -2. So in order to balance the increase with the decrease, you need to make sure that for each Mn being reduced, there is going to be 2 being oxidized. So that when 2 of them are oxidized from +6 to +7, the total change is 2 times +1, which is +2. Right. So that means that we will have a total of 3 Mn, right? So A over here will be 3, right? And 2 of them will be for the Mn's in MnO4, right? Because 2 of them are going to be oxidized and 1 of them is going to be reduced in MnO2. So the 3 Mn's in MnO4, 2 negative, are going to be distributed such that 2 MnO4 negatives are formed and 1 MnO2 is formed. Still, we only need the values of A and C, so the answer is option C, 3 and 2. That's what balances the changes in oxidation number in terms of oxidation and reduction of manganese atoms at the same time. So over here, we need to find the Kp expression for this equilibrium. So that's very simple. We place the partial pressure of the product in the numerator, and we divide this by the partial pressure of one of the reactant, which is hydrogen. This will be squared because we have 2 moles of hydrogen in the equation, and then this is multiplied by partial pressure of carbon monoxide. Now the partial pressure of CO and CH3OH are not raised to any powers because you only have 1 mole of each of them in the equation. So the option that matches this particular Kp expression is option C. So over here we have calcium carbonate reacting with hydrochloric acid. You have calcium carbonate reacting with hydrochloric acid. And it says over here that at regular intervals of time, the volume of carbon dioxide gas given off in this reaction is monitored. Right. So you can see that at 210 seconds, the volume becomes 120 cubic centimeters, and then it stays at 120 cubic centimeters. So as far as this column is concerned, why the rate of the reaction changes with time, right? As you can see that the rate slows down. From 30 seconds to 60 seconds, you have a difference of 30 cubic centimeters. But from 60 seconds to 90 seconds, you have a difference of only 18 cubic centimeters. And this difference in volumes decreases as regular time intervals of 30 seconds keep progressing. So the reaction is slowing down. And the reason for this is fewer collisions between reacting molecules, right? So it's going to be option A or option B, right? Because of fewer collisions, you have a slower rate of reaction. Right. Now, why the reaction stops? Either the calcium carbonate or the hydrochloric acid is used up. Now, which of them actually gets used up? We need to do a calculation of limiting reactant. So first, we find the moles of calcium carbonate. We have the mass, which is 4 grams, divided by the MR, which is 100, that has been given over here. So this gives us 0.04 moles, right? And hydrochloric acid, we find the moles of HCl by multiplying the volume, which is 100. First, we divide this by 1000 to convert to cubic decimeters. Then you multiply by concentration. So this then becomes 0.01 moles. Now, if I write down the equation between the calcium carbonate and hydrochloric acid, this becomes CaCO3 plus 2HCl. This is going to give us CaCl2 and CO2 and H2O, right? An acid and a carbonate will react to give you carbon dioxide, water, and a salt. Right. So over here we have 0.04 moles of calcium carbonate. Now, according to the ratio, which is 1:2 for these two guys, if I have 0.04 moles, I should have twice that amount of HCl, which is 0.08. But in reality, I only have 0.01 moles by using volume times concentration. This is greater than the 0.01 that I actually have. So that means I did not have enough HCl to use up the calcium carbonate, and so the calcium carbonate is in excess, and so the HCl is the limiting reactant, and so it is the HCl or hydrochloric acid that is used up. So option B is correct. So this question was not as easy as it looked. All right, have to be careful and perform relevant calculations. So which statement about ideal gases is correct? Right, so they're talking about two things: particle volume and intermolecular forces. So for an ideal gas, because this is the perfect ideal situation, particle volume has to be 0, right, compared to the volume occupied by the gas itself, and the intermolecular forces also have to be 0, right? These are the two properties of ideal gases, and so option C is the one that correctly describes it: 0 particle volume and no intermolecular forces. So mixture of gases consists of 12 grams of hydrogen, 42 grams nitrogen, and 4 grams of helium. What is the mole fraction of hydrogen? Now, you might be tempted to use these masses directly to find the fraction, but remember they've asked for mole fraction. So first convert the masses to moles and then find the mole fraction. So in this case, for hydrogen, divide the mass, which is 12, by the MR, which is 2. That gives you 6 moles. For nitrogen, you have 42 grams, which is your mass. You divide it by the MR, which is 28. So this turns out to be 1.5. And for helium, the mass is 4. The AR of helium, because this is a noble gas, we go for AR, is 4, so this is 1 mole. Now that you found the moles, you find the mole fraction of hydrogen, right? You divide the moles of hydrogen, which is 6, by the sum of the moles of all the gases, so that's hydrogen plus nitrogen plus helium, right? So this gives us an answer of 0.71, so this will be option C, 0.71. So what's the definition of the bond energy of the BR-BR covalent bond, right? So remember that bond energy is always defined as the energy required to break a bond, right? And it will always be to break 1 mole of the bond, right? And the bond needs to be in the gaseous state, right? So that's the definition of bond energy, right? So the energy required to break 1 mole of BR-BR bonds in the gaseous state, this is option C, and this is in fact the correct definition. We're not going to get bond energy from the liquid state, right? And we do not want to produce 1 mole of bromine atoms. We want to break 1 mole of BR-BR single bonds. Producing 1 mole of bromine atoms, this is actually atomization, not bond energy, right? And that too, we need gaseous bromine atoms. So 1 mole of bromine atoms in the gaseous state. This is the definition of the atomization energy of bromine, right? So this is option C, the bond energy of the BR-BR single bond. In this question, we need to compare relative melting points of these 4 elements against their relative electronegativities. So we know that electronegativity increases across a period, right? So the order of these points, horizontally speaking, has to be magnesium followed by aluminium, then silicon, then phosphorus, because when you move from the left to the right across the periodic table, the electronegativity has to increase, right? So these are the only two options that consider this. So we're only going to stick to these. Now, as far as melting point is concerned, we know that silicon out of all of these will have the highest melting point because it is a giant molecular structure, right? And phosphorus will have the lowest because of the fact that it has a simple molecular structure. And magnesium and aluminium obviously will have melting points that are in between them because they are both metals, right? They both have metallic structures, giant metallic. And so it's option B that gives the correct trends in both properties across these four elements. So the excess of MgO is shaken with water. The resulting mixture is filtered. This is filtrate W. Now, MgO, when it is mixed with water, it forms magnesium hydroxide, right? And 2 drops of dilute sulfuric acid are added and any observation is noted, right? So when sulfuric acid will be added, obviously, this will form MgSO4 and H2O. And we know that MgSO4 is soluble salt, so there will be no visible observation as such, right? The same thing is done with the barium oxide. The barium oxide forms barium hydroxide when it reacts with water. And when it is reacted with sulfuric acid, it's going to give us barium sulfate and water. And we know that barium sulfate is not very soluble. It is going to be a white precipitate, right? So now, out of these 2 hydroxides, we know that barium hydroxide will be more soluble, right? Both of them are in aqueous solution, but because barium hydroxide is more soluble, it will dissolve more easily to give a higher concentration of hydroxide ions, and so it will have a higher pH, right? So filtrate X is going to be the filtrate with the higher pH, which is more alkaline due to greater concentration of hydroxide ions. And when we add sulfuric acid to this filtrate X, we're going to get a white precipitate of barium sulfate. So this is going to be option D. So magnesium carbonate is placed in 2 crucibles. The sample in crucible R is heated until there is no further loss in mass, then allowed to cool. So basically, this is going to be decomposed thermally to give you carbon dioxide, that is the cause of the loss in mass, and we have MgO. The sample in crucible S is left unheated. So in crucible S, you're just going to have MgCO3, plain and simple, and in crucible R, you're going to have MgO that is left over and CO2 is lost. So dilute hydrochloric acid is then added to both crucibles. Which observations are correct upon doing so, right? So when you add it to crucible S, which contains MgCO3, obviously this is going to result in the formation of carbon dioxide, right? So gas is produced. In the case of crucible R, MgO will react with HCl, but that will not produce any gas, right? So crucible R has no gas produced, and in crucible S, a gas is produced, right? Because in crucible R, you have just MgO reacting with HCl, and this is going to give you MgCl2, which is a salt, and water, so no gas is produced here in crucible R, but in crucible S, you have MgCO3 that was untouched, reacted with HCl. This is going to give you MgCl2 and H2O and CO2. And this is the gas that is produced. So when concentrated sulfuric acid reacts with sodium iodide, the products include sulfur, iodine, hydrogen sulfide, and sulfur dioxide. Which statement is correct? Now over here, iodide ions are a strong reducing agent, right? These are a strong reducing agent. What will happen is that the sulfur in the sulfuric acid in H2SO4, this has an oxidation state of +6. This is going to be reduced. So sulfur has an oxidation state of 0. Add hydrogen sulfide. In this, sulfur has an oxidation state of -2. Add sulfur dioxide. Sulfur has an oxidation state of +4. So in all of these cases, sulfur has a lower oxidation state than +6. Right? So option A, hydrogen sulfide is the product of a reduction reaction. This is correct. Right? Iodide ions are stronger oxidizing agents than sulfate ions. Nope, this is going to be reducing agents, right? Sulfur atoms from the sulfuric acid are both oxidized and reduced. Nope, they are only reduced. And sulfur atoms from the sulfuric acid are oxidized to make sulfur dioxide. Nope, they are reduced to make sulfur dioxide, as we have already seen. So solution of sodium hydroxide reacts with 3 moles of chlorine under certain conditions. The reaction produces 5 moles of sodium chloride. So if I react sodium hydroxide with 3 moles of chlorine, this is going to give me 5 moles of sodium chloride and 1 mole of X, the only other chlorine containing product, right? So this other chlorine containing product actually will be NaClO3, right? And the final product is H2O. We have 6 NaOH, right? And we're going to have 3 H2O over here, right? So we know that if we have hot concentrated NaOH, this will react with chlorine to give you 5 NaCl and NaClO3. The other case of cold dilute NaOH will give you NaClO, but for that, we know that NaOH will only react with 1 mole of Cl2. That will be NaOH reacts with 1 mole of Cl2. This will give you NaCl, and it will give you NaClO and H2O, and this will be 2 moles of NaOH. This is for cold NaOH, and this is for hot NaOH. All right, so these are the 2 situations covered. So redox reactions are common in the chemistry of group 17 elements. Which statement is correct? All right, so bromide ions will reduce Cl2 but not I2. All right, so yes, this is correct because bromide ions are actually pretty strong reducing agents, right? And so they will reduce chlorine to become chloride ions, but iodine will not be reduced to produce iodide ions, right? Because bromine is in between chlorine and iodine, right? And bromine is basically less reactive than chlorine, so bromide will convert chlorine into chloride ions, but because it is more reactive than iodine, it will not convert iodine into iodide ions. It'll stay as bromide ions. Which statements describe a trend in period 3 between every pair of adjacent elements from sodium to chlorine, right? So option A is straightforward. The atomic radius decreases because the nuclear charge, it increases, and the other 2 factors, which are namely distance of outer electrons in terms of number of shells, and the number of shielding electrons, they remain the same, and so it'll be in fact the atomic radius that decreases, right? For the other factors, ionization energy, this generally increases, right? Barring some exceptions. The melting point, it has an up and down trend, as we've already seen in question 17. The electrical conductivity increases, well, not really. It increases between the metals, but then there's a sharp decrease when you go to the non-metals. So nitrogen forms polluted oxide Y in a car engine. Further oxidation of Y to Z occurs in the atmosphere, right? So if I say that polluted oxide Y is nitrogen monoxide, that this reacts with half a mole of oxygen, right? And this will give us NO2, right? And this will be polluted oxide Z. So Vin's statement is correct. Compound Z does not further react in the atmosphere. This is incorrect. It will actually react to form acid rain by oxidizing SO2 to SO3, right? A molecule of Y has 15 electrons, right? So over here, you have 7 electrons in nitrogen and 8 in oxygen, so that adds up to give you 15 electrons. So this is correct, right? The oxidation number of nitrogen increases by 1 from Y to Z. Over here, the oxidation number of nitrogen is positive 2, right? And over here, it's positive 4. So no, it changes by plus 2. Y is a nonpolar molecule. Well, no. Nitrogen and oxygen have different electronegativities, so it's going to be a polar molecule. So both of these options are incorrect. So let's begin with the organic chemistry questions in this paper. So important instruction says structural and stereoisomerism should be considered when answering this question. Right. So each of the following carbonyl compounds is reacted with NaBH4. So automatically this means that this is going to be a reduction reaction, right? So the product of each reaction is heated with Al2O3 at 600 degrees Celsius, giving either only one isomer or a mixture of isomers. So which carbonyl compound will produce the most isomers? The second reaction with Al2O3 at 600 degrees Celsius, this is dehydration. So remember that a carbonyl compound, when it is reduced, it will give you an alcohol, right? And that alcohol is then dehydrated using Al2O3 to give you an alkene, right? So let's look at all these options in turn. So you have butanol over here. So you have 1, 2, 3, 4 carbon atoms. The one at the end is the aldehyde group, right? So this is simply then converted into butanol. We have OH over here and H over here, right? So this happens after step 1, the reduction, and then in the dehydration, what happens is that the OH is lost from this carbon atom and an H is lost from its neighboring carbon atom to form an alkene, right? And then as a result, this is going to give you C, 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 double bond C. And over here, this is bonded to 2 hydrogens, right? And this is bonded to 1 hydrogen. So this is going to give you just 1 alkene because this carbon atom bonded to OH only has 1 neighbor, which is bonded to H. So this is going to give you just 1 alkene over here, and because this carbon atom is bonded to 2 hydrogen atoms, these groups are the same as each other, so there are no cis-trans isomers for this, and so this is only going to give you 1 isomer, right? So the product is only 1 isomer, there's not going to be any other isomers. Let's look at butanone. So butanone basically differs from butanol only in the fact that you have C double bond O in the second carbon atom. There's no other possibility for this. So after reduction, you are going to get a secondary alcohol like this. And now you have two neighbors to the carbon bonded to the OH. You have this neighbor and this neighbor. So you could get rid of either this H with the OH during dehydration, or you could get rid of the OH and this H. So you're going to get two products, right? So the first product is going to be C, C, double bond, C, C, right? And the second is going to be C, 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 double bond C. The double bond is at the end. Now, in the first product, you have two H's over here and two CH3 groups. And each carbon atom is bonded to two different groups, the H and the CH3, and the same goes for the other carbon atom. So this can have cis and trans isomers. Right now I've drawn the cis, so there's going to be a plus trans isomer for this. And over here in the second product, because this carbon atom is just bonded to two hydrogens that are the same as each other, so there's no cis trans for this, right? So that's a total of 3 isomers, right? So the first product has cis trans isomers, so that's 2. And the second product with the double bond at carbon atom number 1 over here, instead of at carbon atom number 2 over here, you have just 1 isomer. There's no cis trans for this. So 3 isomers for butanone, right? Now for pentane 3-one, we have 1, 2, 3, double bond over here, 4, 5, but this is reduced. You get 1, 2, 3. Over here we have the OH, 4, 5, right? And once this is dehydrated, you could either get rid of the H over here or over here, right? So once you form both of these products, you get C, C, double bond, C, 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 right? So over here, the double bond is at carbon atom number 2. Now, if you were to do the other product where this H is gotten rid of, you get C, 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 and over here you'll have a double bond, and then over here. Now, this is also at carbon atom number 2, so these are both the same as each other, right? And because these are the same, they will count as just 1 isomer, but in the double bond, you have both carbon atoms bonded to 2 different groups. This one is bonded to CH3 and H over here, and this is bonded to H, and this becomes CH2, CH3. So over here, I've drawn the cis isomer. This will have plus trans isomer, right? So over here in total I have 2 isomers. All right, and finally propanone. Propanone, we already know that the double bond O is on the second carbon atom. Just going to skip to the OH after the reduction, and then after dehydration, it doesn't matter whether you get rid of the H from this neighbor or the H from this neighbor. It's both of them are going to give you the same alkene, right? It's going to be C, double bond C, single bond C, right? And this carbon atom is bonded to 2 hydrogens, so no cis trans isomers for you. So this is just going to be 1 isomer. So this is an example of a question that is very detailed, and you have to run through all the options, but at the end of the day, you have 1 isomer here, 2 isomers for option C, 3 for option B, and just 1 for option A. So option B, after all this effort, is the correct answer. So we have cortisone shown over here, and 3 chiral centers have been marked with asterisks over here, here, and here. Now, how many other chiral centers are present? Now, for this, what I'm going to do is I'm just going to count the carbon atoms for which you can see at least 3 bonds in this skeletal formula, right? So, for example, this carbon atom, you can see 4 bonds. So this is a chiral center. This carbon atom over here is not going to be a chiral center because it has a double bond. Has to be bonded to 4 other atoms, right? These 3 have already been counted, and I have this carbon atom that's bonded to 4 different groups. I have this carbon atom as well, right? And there seem to be no other carbon atoms for which I can see at least 3 bonds in the skeletal formula, right? So I will have 3 other chiral centers in this case. So the alkene is reactive with acidified manganate 7 ions. The organic product has a relative molecular mass greater than that of the alkene by 34. So 34, if you look closely, this is the same as that for 2 OH groups, right? So 2 into 16 plus 1. 16 is for O, 1 is for H. So this gives us 34. So this means that we have 2 OH groups that have been added to the alkene. So that means this is going to be a diol. So an alkene forms a diol with manganate 7 ions when they are cold and dilute. So this diagram shows a short length of addition polymer chain. The polymer has a relative molecular mass of approximately 10,000. So how many monomer units have been joined together? So what we do is, in an addition polymer chain, we split the section of the polymer chain shown into pairs of carbon atoms, right? And we know that each pair of carbon atoms once had a double bond between them, right? And so the monomer turns out to be ethene C2H4. So when I find the MR of C2H4, it turns out to be 2 times 12 plus 4. So this is going to be 28. Then what I do is divide 10,000, the MR of the polymer, by 28. This gives me around 357, which is approximately 360 monomer units, which is option B. So lactide is an intermediate in the manufacture of a synthetic fiber. Which compound on heating with an acid catalyst can produce lactide? Right. So let's take a look at this. What I'm going to do is, instead of running through all these options, I'm going to go for the reverse, right? I'm going to work my way backwards. You can see over here that lactide has 2 ester linkages, one over here and one over here. Now, the reverse of esterification is hydrolysis. So if I break the carbon-oxygen single bonds, I will get the starting material. So over here, I have this oxygen over here that is bonded to H, so this is OH, right? Then I continue the structure from here. I get C double bond O, and over here this is going to be bonded to OH, right? So this is the acid over here. Now, from here, this oxygen, I'm going to have OH, right? If I continue the structure from here, I'm going to have C double bond O, and I'm going to have OH. So you can see that both of these are the same, right? Both of these are the same compound containing both an OH group and a CO2H group that basically react with each other. Right. So over here, I have this carbon atom is number 1 in the carboxylic acid group. This is number 2. Number 2 is bonded to the OH, right? and this is obviously going to be number 3, right? So there are 1, 2, 3 carbon atoms in this chain. Number 2 is bonded to OH, so this is going to be 2-hydroxy propanoic acid. Propanoic because this is the CO2H group speaking. Prop tells me there are 3 carbon atoms in the main branch, so have 1, 2, and 3, right? This, by the way, is a CH3. And 2-hydroxy tells me that it's carbon atom number 2 over here that is bonded to the OH, the hydroxy side chain. Diols in which both hydroxy groups are bonded to the same carbon atom spontaneously eliminate a molecule of water to produce a carbonyl compound. Which compound is hydrolyzed to form a product that gives a positive reaction with 2,4-DNPH, but not with Fehling's reagent? Right. So basically need to find a compound that gives a positive result with 2,4-DNPH. So that means it's definitely a carbonyl compound, but not with Fehling's reagent. So that means we're looking for a ketone, right? So that means that the carbon atom that is bonded to the 2 OH groups has to be a carbon atom that's not at the end of the chain, right? So over here, all of these options A, B, and C have a carbon atom that is numbered 1. That will not do. So we're going to go with option D, right? 2,2-dibromopropane, right? So basically 2,2-dibromopropane is going to give you this particular alcohol, right? With 2 OH groups bonded to carbon atom number 2. Right, the BRs were replaced with OHs by reacting with aqueous sodium hydroxide, nucleophilic substitution, right? And then these will be eliminating a water molecule. So this complete OH is removed with an H over here, and then this forms a double bond with the leftover oxygen here, right? This forms propanone that will give a positive result with 2,4-DNPH and orange precipitate, but it will give nothing with Fehling's reagent because it is a ketone, it is not an aldehyde. So X and Y are the reagents required to convert 1-bromopropane into butanoic acid in the following reaction. What are the correct identities of X and Y? So Br over here needs to be replaced with Cn, so X will obviously be ethanolic KCN. So KCN in C2H5OH, that's ethanolic KCN, and Y basically requires Cn to be hydrolyzed to give you this carboxylic acid group. And to make sure that it remains CO2H and does not react further with the catalyst, you have to make sure that Y is not an alkali, because otherwise this will react with the carboxylic acid group. So Y has to be an acid, so it does not react with the acidic CO2H. So it's going to be option C. So Q is a compound with the molecular formula C4H10O. Q can be oxidized with acidified potassium dichromate 6. Q cannot be made by reducing a carboxylic acid with LiAlH4. So if it cannot be made by reducing a carboxylic acid with LiAlH4, then that means that basically Q cannot be a primary alcohol derived from a carboxylic acid, but it can be an aldehyde, right? And aldehydes can be oxidized, right? But over here in all of these options, you only have alcohols, right? So you have OH, 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 and OH. So these are all alcohols, right? So that means that Q will probably not be a primary alcohol, right? It can be oxidized. So that means it is either primary or secondary. It cannot be tertiary. And Q cannot be made by reducing a carboxylic acid with LiAlH4. So that basically means that primary is out of the question. So it has to be a secondary alcohol. So out of all of these options, A is your only secondary alcohol because OH is bonded to C, is bonded to two other carbon atoms. So a sample of 2.3 grams of ethanol is mixed with an excess of aqueous acidified potassium dichromate 6. The reaction mixture is boiled under reflux for 1 hour, right? So it says the yield of the product is 60%. So ethanol over here, when it is oxidized completely, it forms a carboxylic acid. Specifically, it will form ethanoic acid, right? Form ethanoic acid. And over here, first of all, what we'll do is find the moles by dividing the mass by the MR. This is going to give us around 0.05 moles. Right. Now, it says the yield of the product is 60%, right? First of all, we find the theoretical yield of ethanoic acid, which is our product. So what we do is we find the mass, which is the moles. And remember, the moles are going to be the same because there's a 1-to-1 ratio between the ethanol and ethanoic acid. Right, so 0.05 times the MR. So in this case, it will be 12 times 2 plus 4. 12 times 2 for the carbons, 4 for the hydrogens, plus 16 times 2 for the oxygens. So all of this gives us 3 grams, right? So this is your theoretical yield. Now the formula for yield, the percent yield, is actually the actual yield divided by theoretical yield into 100%. So if I plug in the values, this is 60, actual yield is unknown, theoretical is 3 times 100, and so X turns out to be 1.8 grams, and so it's going to be option C. Compound R gives a positive test with alkaline aqueous iodide. Compound R does not display stereoisomerism, right? So for alkaline aqueous iodide, there are only 2 groups, right? There is CH3CO, or it is going to be CH3CHOH, right? Now, out of all of these options, we have option A that contains the relevant group, and we have option C, right? All right. And out of these 2 options, option C actually does have a chiral center. It does display optical isomerism because of this carbon atom here that is bonded to hydrogen, and OH is CH3 and a CH3 C double bond O. By the way, this CH3 CHOH is also responsible for alkaline aqueous iodine, giving a yellow precipitate. So it's going to be option A because it has the required group and it has no chiral centers. So citral over here is being reacted with an excess of hydrogen over nickel catalyst. So the only thing this will reduce is the double bonds and convert them into single bonds. Hot concentrated acidified manganate 7 under reflux will oxidize this aldehyde group, right? And this will give us CO2H, right? Now you might be tempted to think that because we have hot concentrated KMNO4, that is going to react with these double bonds, but remember we removed them using hydrogen over nickel catalyst, so the only group that will react with KMNO4 is the aldehyde group, converting it into a carboxylic acid. So this is going to be option B. So P and Q are alkenes, they're geometric isomers of each other, so which statement is correct? So P and Q give different products with hot concentrated acidified potassium manganate 7. Nope. Alkenes, which are geometric isomers of each other, will have the same chemical reactions. They will also have the same empirical formulae. and they will have same functional groups, right? The only thing that will be different is the skeletal formula, right? Because that shows the arrangement of the groups bonded to the carbon atoms in the double bond, which thus shows geometric isomerism. So over here we have 3 halogenoalkanes, 3 chloroalkanes that react with aqueous sodium hydroxide. It's going to be nucleophilic substitution, right? So which statement is correct? CH3-2CH, CH2Cl reacts with NaOH by an SN2 mechanism. Yes, because SN2 is for primary halogenoalkanes, and over here you can see that Cl is bonded to a carbon that is further bonded to just one other carbon. This is primary, so this will be correct. For which mixture is the observation described correctly? Now we'll have to go through all these options. So pentanal reacting with Felling's reagent, blue solution changes to orange red precipitate. Yes, this is correct because Felling's reagent is a blue solution of copper 2 sulfate. This gives us a red precipitate of Cu2O because the copper 2 ions have been reduced, and the pentanal is an aldehyde that gives this positive test result, and so it is oxidized to pentanoic acid. Which statement is correct? So it says that butanoic acid can be used to form propyl propanoate in a single reaction. Nope, because this is butanoic acid, you will have to reduce the number of carbon atoms in this carboxylic acid somehow before converting it into an ester. The empirical formula of butanoic acid is the same as its molecular formula. Nope, because the molecular formula for this is C4, because we have 3 plus 1, that's 4. H8, because it's 7 plus 1, H8O2. Simplify this to C2H4O. So empirical and molecular formula are not the same. Each of C3H7OH and C3H7CO2H reacts separately with NABH4. Okay, so NABH4 only reduces carbonyl compounds. It will not reduce this carboxylic acid, right? So it will not react with NABH4. It will only react with LiAlH4. So each of propanol, which is C3H7OH, and butanoic acid react separately with sodium metal. Yes, that is correct. And both of them will release hydrogen gas while they're at it. So we have a final question, and this shows an infrared spectrum of compound X, and it consists of carbon, hydrogen, and oxygen only, right? It has only one functional group. Now, if you look at the absorptions, we have one absorption over here. Now, if I draw a line from the lowest point of this absorption to the x-axis, this is at around 3000, right? And I have another absorption over here, which is at around 1700. So at around 1700, that shows we have a C double bond O. And at around 3000, we have OH, right? So we have these two bonds, but it says only one functional group. So it cannot be an alcohol, it cannot be an alkene, it cannot be an aldehyde or ketone. The only option that includes both of these bonds, C double bond O and OH, is option C. Congratulations on making it to the end of the video. We are done finally. So this was our first video of the SolveIt series. If you like this kind of video, do leave a like and leave a comment down below on what past paper we should do next. And do share this video and subscribe to the channel, and inshallah I will see you in the next video.